2001, question 3, part B. This was an unusual question 3 because it combined elements from other questions as well. And what you have happening here is a ball dropping onto a plane from a height h. So that part of the question is actually a linear motion question, something dropping with acceleration g from a height h. So we call that part 1 of our question, where it drops. And then the part 2 is the collision with the plane. So this is like a question 5, a part of a question 5, an all question 5, a collision with a surface. And then of course there's the rest of the question. When it rebounds, it now acts as a projectile going down a plane. So that's the third part of the question, a projectile going down a plane, which is even a bit unusual because normally in most questions they go up. So there's a lot of unusual elements to this question, and that's why we need to break it down into 3 parts. So that's how we're going to tackle it. Part 1, we're going to do linear motion. Part 2 is a collision, and part 3 is a projectile down a plane. So let's do that. And let's start with part 1, linear motion. So linear accelerated motion. Once you realize it's linear motion, it's a fairly straightforward linear motion problem because we have all that we need. We have, for example, it's dropped, so u is 0. If it's dropping under gravity, free fall, well, the acceleration is then going to be g, and we're told the height, or s, is h. Now, bearing in mind that the next part of the question is going to be collisions, we need to know the speed at which we collide. So we need to know the finishing speed. This is the v for our linear motion part. It's going to be the u for the next part. So we need to calculate this v. And now it should be obvious what equation to use. It's v squared is equal to u squared plus 2as. V squared is equal to 0 plus 2 times g h. So v turns out to be the root of 2gh. And that's part 1 of the question finished. As such, that's the linear motion part done. Now the second part of the question is the collision part. The best thing here is to draw the diagram again and show the collision. Let's have a closer look, and we'll see again that there's an object coming in here vertically with a speed u, and it bounces off of the plane here at this point with some velocity v. Now, for collisions, the first thing we must always do, especially on a slow plane like this, is to be clear on what our x-axis is and what our y-axis is. And we always choose these to make life as easy as possible for ourselves. The angle is 30 degrees, and we will pick the x-axis along the slope because this makes life easy. We're moving this way, moving down the slope, so pick the x-axis as moving down like this. And the y-axis is perpendicular. The y-axis is perpendicular, and we put that in there. And the next thing we do is, once we have an x and a y-axis defined, we must resolve along those axes. Let's take our u first over here. And we will resolve it. Y component and x component. By trigonometry, this is 30 degrees, and this is u, and this is u cos 30, and u sin 30. cos 30 root 3 over 2, so that becomes u root 3 over 2, and the sine 30 is a half, so this becomes u over 2. So we'll just fix that there as u over 2. U over 2. And now we'll do the same for v over here. So v is going off in this direction. And again the x component and the y component. Now to proceed to the next step, we need to make an observation about the force at the point of impact. And to emphasize this, let's do the force in a different color. When a sphere hits a surface like this, the surface acts as a tangent, and the force of impact is through that point of contact at right angles to that plane. So we'll put that in here as F. And that is the direction of the force along the y-axis. And if the force is along the y-axis, of course, that means there is no force along the x-axis. And according to Newton's first law, if there is no force along x, that means that there is no change in velocity or speed along x. Again, that's as a result of Newton's first law. And if there's no change in velocity or speed along x, well, that means in turn that we can safely say that this component along x here after the collision is the same as before, which is u over 2. So it's u over 2, and if it's u over 2, that means that we'll just call this one for the moment, we'll call this one vy, we'll call this one vy. And that's the components done. Now the last thing we need to do is to apply Newton's experimental law for the collision, and since the only change is along the y-axis, we only have to apply Newton's experimental law along the y-axis. So minus vy over u in the y direction. And e is a half, so we get a half is equal to minus vy over uy. And uy is this component here. Be careful with the arrow again. It's in the minus y direction, so it's minus u root 3 over 2. And in the y direction. Now those minuses cancel, and we get the result that vy is equal to a half times u root 3 over 2, which is u root 3 over 4.